Hello everyone, Vladimir Alifman, the TACT course, and today we have crossed the equator, for which I congratulate you. In today's lesson we will look more at the syntax of TACT, we will look more about its data types and look at its features. So sit back comfortably and we are starting. Let's start with talking more about functions. As we know, there is several types of function in TACT. We are familiar with such a type as receive, bounce, get functions, just ordinary functions that perform some part of logic inside themselves. But there are also a few more types of functions in TACT. Functions can be global, for example. This means it's taken out of any contract, thus such a function can be used within several smart contracts. Next type of function in TACT is extends functions. They differ in that they can extend an existing data type, and with their help we can create new methods for any data types. How does this look in practice? In this case, we will write a new method for all integers. This will be multiplication, and the main rule of extendable functions is that its argument must be called self, type integer, and the second argument will also be type integer. And here we will return the result of self multiplied by b. Then you can use such a function as follows. Let me write a regular get function, mol result. I'll create one more in the contract variable, num, with type integer. And now for our num, our method mol exists. And it works so that our num becomes self inside this function. That is, if our num had a value of 5, then here would obviously get the result of 25. Also, our extendable function can be mutable. That is, it not only returns a new value without changing the old one, but can also change the existing value. Let's see how this looks like. For this, you need to write a keyword extends, mutates, and I will call it add. I also write the first argument with the same name, self, type integer, and b integer. And here I assigned a new value to self. And I can use it in the following way. Here the main thing is not to confuse self. In this case, self tells us that our smart contract, and then we refer to the variable num. Okay, these are the main types of functions in TACT, but I must say that there is one more type of function. This is a function that allows interaction with contract at a lower level, that is, with the code on fun-c. They look like this, but since we now have a course on TACT, we will not delve into this. Just know that this is also exists. Okay, let's move on. The next thing we will talk about is loops. There are three types of loops in TACT. The first loop is repeat, which has a very simple syntax. We set how many times we will repeat this iteration. After we exit the loop, we will log our variable sum, for which there is a dump method. And by the way, here is another proof that TACT is a young and fast-moving language. At the beginning of our course, there was no support in Blueprint for the TACT language, this functionality. I had to contact the Blueprint developers to add it. In order for us to see the result, we need to go to the wrappers folder, and here we have a compiled CS file, and we need to add a field options here, where debug will be enabled with the flag true. Our code is currently compiling because Blueprint is still on version 0.10, so we will have to update it to version 0.11. Let's do that. Now let's write a test to see that our debug works as it should. We will run the test. Yes, now you can see how you can debug your code. Only here I wanted to test not 1 but I, to make the example a little bit better. Yes, now this is the result I expected. Okay, let's move on. The next type of loop in Thon is the while loop. As you can guess, while works here without surprises. As long as the expression returns true, it works. Once it is false, it stops. Let's check it out. There was a typo here, and we see that the result is the same. Okay, the last loop intact is the do until loop. I think if you already have programming experience, you know all these loops. They should be familiar to you. It's just a matter of syntax. And as you understand, the result here should be also equal 55. Naturally, you have to write it in the test. Okay, we are moving on, and next we'll talk about optional variables and optional fields. To declare an optional variable, a question mark is used. An optional variable means that it can either be the type we specified or the null value. Options can be either variables or fields, such as in structures. Fields in messages can be optional too. And when we are initializing such variables, we also have to specify that they are optional variables. To access an optional field in a message, for example, you need to check beforehand that it doesn't equal null. For example, if we want to receive the message options and from the message we want to get field num to store it into our variable num, we will first check that our message num doesn't equal to null. Only after we are sure that message num has a value, we can access it by specifying 2 exclamation marks at the end. This way we tell the compiler that message none cannot be null. Optional getters can also be used. And as you see, if our type is optional, then we don't need to put 2 exclamation marks here. However, if we wanted to definitely return some value, we couldn't do this way, because beforehand we would have to check that if our value equals to null, then we return, for example, -1. Otherwise, if we didn't fall into this scope, we are sure that our none exists, and with the exclamation marks, we let the compiler understand this. There can be some difficulties when we are working with structures. For example, if we have an optional structure in our storage and we want to extract the num field from this structure, we have to do it through a series of checks. It looks like this. We first check that our structure does not equal null. Then, in case the structure really doesn't equal null, we refer to it and let the compiler know that it has a value. After that, we go to the num field, and our num can also be null. So if we also additionally check that our num doesn't equal null, and Only after such a full check we return this value. It certainly doesn't look nice, but at the moment that's what we have. And maybe in the future versions of the language this issue will be corrected. The next thing we will discuss are two methods in Takt which allow working with time and randomness. Time in Takt is represented in Unix format, which is the number of seconds that started since 1970. The method now is used to get the current time. If we want to use logic to freeze funds for a certain time, or logic to accrue interest all over a period of time in our contract, we will use Unix format time. I'll write now two methods that should only work when a certain time has arrived. For example, the first method should only work when 10 seconds have elapsed from the moment the contract was deployed. The second method should work in 10 days. To do this, I will convert 10 days into seconds by multiplying 10 by 24 hours and 60 minutes and finally by 60 seconds. Okay, let's test it. First, I need to build my contract here. I'll do this by setting the debug flag to set this console log. Then I send the transaction. Compilation error. I have a typo here. Okay, once we try to send the message right away, we naturally will not see anything here because our message will return with an error. To prevent it from returning with an error, we need to wait 10 seconds. For this, the first time should be an error. We will not see anything. Then we sleep for 10.5 seconds and repeat the method again. Okay, let's run the test. There is a timeout error here, so we need to increase the timeout for this test. Let's give it 20 seconds. As we see in the console, it actually works. Only one dump, only one log we saw. Okay, we will not check the second one. We will not wait for 10 days, but I'm sure it will work the same way. Now let's talk a little bit about the random function in Takt. I will create two getters through which we can get a random number. And there are two methods in Takt for getting a random number. The first one is randomInt, which simply returns any number in the maximum range. And the second one is random, which takes arguments. Let's just look at the result in the test. Of course, we need to build our contract. And let's also take a look at Unix time. We forgot to look at this in the tests. Okay, I'll skip this test because I don't want to wait 10 seconds. Let's look at the result. Here we see our time format in seconds. and the random numbers we got. It's important to say about random that it's pseudo-random. This means that it can be predicted if you have the initial seed. So if you're writing some business logic that involves random and your finance are staked under random, whether it's lottery or casino game, you need to delve deeper into how random works and take this into account in your business logic. Okay, the last data type, map, which we will look at today. It can be of two kinds. The first, where its k is an integer, and the second type, where the k is an address. The value can be any type, bool, integer, address, or some structure. Maps can be set using the set method. To remove an element from a map, you can also need to set the value to null through set. Also, one map can be completely replaced by another. Let's implement this through sending a message. Also, maps can be completely cleared using the empty map method. And we get the value from the map through the get method. And when we are getting, we must definitely specify a question mark, because our compiler doesn't know for sure if there is a key in this map, or rather if some value is stored by this key. We can also return the entry map using the get function. Okay, I guess we have gone over the syntax of the map, but it has one important feature that I want to demonstrate you in the tests. Let's write another method that allows us to add one element to our map, in which the integer is the key and value is integer 2. I'll write a new message for this, add a new receiver on it, and simply set the value. Also, I'll implement the logic of sending back the remaining Toncoins after paying the commission. Okay, let's go to the tests. Let's also make it so that when we deploy our contract, we also initialize the first map. For this, as an argument, we will pass what we expect to get here, map, with the k integer and the value boolean, and assign the value. Okay, let's build it. Yes, for some reason I specified not k value in the message, but from 2. Let's correct this now. Alright, let's start writing our test. Firstly, how should we add an argument to our contract? It requires a map, but our TonCore library refers to it as a dictionary. Therefore, we need to work with dictionary in JavaScript. So let's obtain it from TonCore and attempt to initialize it. To do this, we need to call the static empty method inside the dictionary cell, which will create an empty dictionary for us. Inside the empty method, we must pass two arguments, the type of key and the type of value. In this case, we should use integer and boolean. We return to the dictionary class, then go to the case field, and here we need to call the begin method, passing the number of bits for this number. The second type is dictionary values bool. Okay, in this way we created our map already on the layer of JavaScript. Now we will also set one value for it. By the key1 we will set the value true. And now we will pass it to our contract. This was needed only so that we could see how to work with a map and a dictionary on the JavaScript side. Now let's go back to the feature I wanted to show you. What I want to show you now is that I want to call this message in large quantities to expand our map to some larger values. I'll do this to demonstrate, to show how the commission will be changed from element to element. That is, you can guess that the commission will also change. It will not be static. Although it seems that we are doing the same thing, we are only recording one element, but no, it's not. Let's see this together. For this test I need another function that will return how much gas I spent on a transaction. Let's write it at the global level. I'll call it getGasUsed. I'll pass the sender as an argument and I will pass the message. My message will be of type any for simplicity, and my sender will be of type sandbox contract treasury contract. I will calculate it in a very simple way. First, I'll get the balance before the message is executed from the sender. Then my message will be executed. And then I'll return the difference in balances before and after the message execution. Let's start writing the test. First, I'll create an array, GasUsed, where I will record the result of each message and how much gas was spent on it. Now I will send my messages in a loop. Let's start with 100 messages. Here I will call my function getGasUsed, where the first argument I will pass the deployer. Only I need to get it from here first. Let's copy it from here. I pass the deployer and the second argument will be a function in which I will implement the sending of a message. Everything as usual, I use the map contract, then the send method, and here I add the deployer. I'll pass the arguments such as value and the message add, and here a key and a value will be the same. That is, I will now start a loop. On each iteration I'll send messages where the key and the value will be the same value. That is 00, 11, 22 and so on. It doesn't matter much what values are here, it's important to show how the amount of gas increases. And let's proceed. I'll be simply adding to the GasUsed array results. We will record how much gas we paid during each transaction. And at the end we will simply output the first and the last transaction in the console. And also for clarity, let's output the entry map that we got. Now let's run the tests. In this part we also need to add async await to avoid unforeseen results. Let's have a look. As we can see, we have all our values from the map, which we can access via values method. And we can also see how much gas was spent on adding the first element and the last one. Let's make it more readable. I'll convert this from nanotoncoin to toncoin. I'll comment out all the values and we will just look at the gas. As we can see, the first message cost us 0.0015 toncoin. And the second message was already 0.0018. It became more expensive. As you can guess, if we increase the number of elements added, the last transaction will also be more expensive than 0.0018. Yes, it has indeed increased. And since adding a new element to the map becomes more and more expensive, it primarily tells us that using a map for large data structures is simply inefficient. Secondly, it's not unlimited, meaning there is a point when we already have billions of entries in our map. Adding another element might cost us more gas than the gas can fit in one block, and then we will hit a ceiling, and our system will no longer be able to operate. This is another very important feature of developing smart contracts in Takt or Ton. There are no such unlimited structures here. But don't worry, there is a way out and you can create unlimited structures. It just needs to be done a bit differently. Once we study this, we will be able to write our first token on the Ton blockchain. We will do this in the next lessons, but that's all for today. Thank you for your attention, goodbye, and see you soon.